quantify that as we use H. So LIGO discovered last year, or 2 years ago, was 2 inspiraling black holes. Okay? Those inspiraling black holes produce gravitational waves, and the strain that they produced was 0.20 zeros and a 1, 10 to the minus 21. Okay? And that corresponds to a difference of about 1 human hair between us and the nearest star system, Alpha Centauri. Tiny. I mean, it's a testament to the how incredible LIGO is as an instrument. And the waves that led to that oscillated, that oscillation that I tried to give you an image of, was about 100 times a second. Okay. So what are we after? We are after gravitational waves produced from the extraordinary densities at the birth of the universe. It was back then much more compact and hot. Their strains could be as large as a part in 100,000. Right? Next to what LIGO measured, these are huge, right? They're enormous. The oscillation frequency, though, is very roughly, sort of 10 cycles in the age of the universe. Okay, so these are really they're fixed on the sky. And if we detected them, and we will detect them in the microwave if we can, we'll see them in the microwave background, we'll get to that in a minute, they will provide us a connection between the quantum world, the same world that gave rise to all the fluctuations we see now, and gravitation. It should be amazing, certainly test for cosmology, and a link between, if you will, Einstein and Bohr that we have been searching for in physics for 100 years. Okay, so let me show you what it is that we actually look for. So this is a video made by a student who's now a sophomore, Riley Bova. And when it starts the picture, it'll start out in our galaxy. Our galaxy is about 100 billion stars, and we're about 2/3 of the way out from it, 25,000 light years to the center of our galaxy. And then it's going to zoom out. Can you start the video and the music if it comes through? It's rocking right off. All right. And so see, you're going to start off in the galaxy, and I want to give you a sense of the scales and distances that we measure. So there's home. I think it's centered on Stanford there. So. Okay, so those objects right there, these are some of the things we measured with our telescope. Those are groups of roughly 1,000 of our galaxies. Okay, so take 1,000 times 100 billion and put them there, and that's what we see. And you can see how far away they are. Those are called clusters of galaxies. And there we go. You see, you start to get out, up near 1 billion light years, right? Closing about, we're seeing out to 1 billion light years. The blue ones are from the Planck satellite. The red ones are from an experiment that we do. Actually, the LIGO source was about 1.2 billion light years away. And you see, we zoom out. Telescopes are like time machines. As we look out, we look back. We keep looking out much further than those fixed objects we can see, and we look out to the cosmic microwave background. This is here. Okay, here's mine. So what are we looking for? What we're looking for, and you can see it's embedded in this black space, and we really think of it like that. These are gravitational waves that pervade space at scales larger than our observable universes, right? This is set by the age of the universe times the speed of light. And what these do, that same strain, if you will, these squeeze and expand the universe, the observable universe. And they're not all the whole size of the beach ball, but they can be like dimples in the beach ball, a fraction of it. Okay, so that's what we're looking for. And what they do, and the new signature, is they produce a characteristic pattern of polarization in this image. And so we're measuring the sky, not in temperatures you saw before, but we're measuring the sky with, if you will, polarized sunglasses for the microwave background. Right? So that means if you have polarized sunglasses and you look at the sky, and you turn them, it will look different. Okay, you take the glasses off, you turn it, it looks different. Okay, so we're looking for that, but we're doing it in microwaves. Okay, so how do we do it? Here's another, if you can click this video. So we have a set of telescopes. It's actually the group at Stanford, Charlie Kuhl's group, is doing this at the South Pole. There's another set of telescopes in Chile. This is now led up by my colleague Suzanne Staggs at Princeton and Mark Devlin at Penn. And so this is at 17,000 feet in northern Chile. And we build these telescopes, and you'll see there's a community of them. And we have turned out, you can see the far one there, actually, Chuck Bennett and Toby Merritt are working on that one, and another group at Berkeley and San Diego are working on the one off to the left. And we're searching for this polarized signature in the sky. So, and very recently, Jim and Marilyn Simons have given us we're very generous and have given us funds to expand this whole effort and build a whole infrastructure up there. So in 10 years, when we found these and someone comes back and gives a talk, right, you'll see a much larger, you'll see a larger setup there. Okay. So how do we actually do this? What's involved? And what as I said, we're looking for this polarized signature. And when we did the WMAP, when we did that, we of course did it from a satellite, and we did it with roughly 40 detectors. And this gives you an advanced 40 detectors at round numbers, 100 degrees above absolute zero. We're now working with thousands of detectors. This is how much things have evolved since not too long ago. We're now working with thousands of detectors cooled to 100 millionths of a degree C above absolute zero. These massive arrays. And we're building up to look at the sky in 40,000 detectors all at once. And to search for this characteristic pattern. And I'm just showing you a few pictures there. On the bottom is a sort of typical detector system size. And just typical cryostats. This is what we build. It's a lot of fun. And there are a lot of groups around the world doing it. And so what is it then that we want to measure? Again, this is a simulation by Brian Keating and colleagues.